Okay, class, this is the final installment of the functional group survey for infrared spectroscopy. Today we'll be looking at amines and then all of the other sort of designer functional groups, sulfur containing functional groups, other nitriles, that type of thing. So amines, let's look at this first. So we've got a hint of what the amines would look like when we looked at the amide infrared spectrum. The key part for the amines is both primary and secondary amines have NH stretches down in the same region that you would see the OH stretches. And if the amine is a primary amine, like this amine here, where there's one alkyl group and two protons, you will see a double peak. If it's a secondary amine where there's two alkyl groups and one proton, you would see a single peak. These peaks aren't as large as the OH peaks, but they're quite distinctive in this area. And so with amines, those are the main things that you'll be looking for, these peaks here. You can look for confirmation things like the NH bend over here. So it's quite a broad peak. It's just below where the carbonyls would fit in. The NH stretch is in the same, between 1,000 and 1,350 or so. This one's quite small. There is a large out of plane bend for the NH protons that is quite broad. Now, this only will apply for primary and secondary amines. Tertiary amines, which have no NH bond, you won't see any of these peaks here. Right, that's the main distinctive feature. These stretches right here. I think I've got an example of a tertiary amine. Here's a secondary amine, so here's the single stretch. CN peak around between 1,000 and 2,000, 1,000 and 1,200. NH out of plane bend, very broad, can't miss that. And of course, the CHs and C stretches and bends like normal for normal aliphatic alkane there. Here's an example of a tertiary amine. So in here, you notice because there's no NH, those peaks are missing. You still see the CN stretch. So with the absence of an NH stretch or an NH out of plane bend, if you know you've got an amine, it's probably a tertiary amine. Nitriles. Okay, so carbon triple bonded to nitrogen. This has got a wonderful diagnostic peak, which appears in a region that but there isn't a whole lot of other spectra, or absorptions, I should say. 2250, this carbon-carbon triple bonds, if they exist, come out around here as well. But this is a polarized bond, so you're gonna see that, and it's this beautiful, sharp peak. So that is the diagnostic peak that you'll be looking for a nitrile, the presence of a nitrile. If it's there, you can't miss it. Now, there are some functional groups that are similar to nitriles, similar to ketenes, and these are the isocyanates or the isothiocyanates. So remember, in both of these instances right here, this carbon is sp hybridized. So and they show up in the similar region as a sp hybridized carbon here. 2270, 2125. Of course, we could figure out why this is lower based just upon the reduced mass of oxygen and sulfur. So that's there. So here's this very broad isocyanate stretch, and it's in a region where there isn't many other things, so you can't miss that if this is present in your molecule. Now, this example here is an aromatic, so you see the aromatic monoubstituted CH bend, and you see the aromatic stretches, and this would be the fingerprint region here for the monosubstituted aromatic. Nitro compound. So another popular functional group we'll see a lot with regard to nitrogen. So remember this nitrogen, oxygen, this system is delocalized. So you've got resonance structures where we move these electrons here and then we'll move those pi electrons up. So technically these bond lengths are, it's not a double bond, it's not a single bond. Each of these is basically a bond and a half. And there's two stretches for each one of these, one at around 1600 or a little bit less, and the other one just under 1400 here. So you'll see these two distinct peaks for the nitro group. Another example here with the aromatic, again, the two peaks. So there can be two stretches for these types of vibrations, a symmetric stretch and an asymmetric stretch. And you'd see these two different peaks there based upon that. So for the nitro, these would be the main peaks to be looking for, because you'll see the two of them together. And of course, with an aromatic substrate, because of the conjugation, the wave numbers is reduced, which, as we've seen for all of the examples so far. So for the nitro group, look for these two broad stretches. Amino acids, carboxylate salts, and amine salts. So if you do any work with amino acids and you get an infrared spectrum, they are pretty messy, I should say, because they've got all of the functional groups that make big, broad absorptions. And so NH stretches. So for here, the NH stretches are broad and they cover basically the same area as carboxylic acids. They basically move over into where the CH stretches would be. So this is a very broad stretch. Remember, in this case, the nitrogen's protonated. It's a salt, so it's got 3 bonds to the proton, so it's a very broad absorption. Now, unlike a carboxylic acid, this is a carboxylate, so we've got a negative charge here. So this means that there's actually, and this is of course just like the nitro group is in resonance. You can move these here and move that there. So this is a bond and a half. This is a bond and a half. So you see 2 carbonyl stretches, one at 1600, one at 1400. So these are shifted down because the force constant is lower, right? It's a 1.5 bonds as opposed to a pure double bond. So here's one, the other is here. So you can see that this has become quite a mess, and you've got your NH bends in this area as well. So this is why I say these sort of compounds are quite messy. Sorry, I didn't mean to do that. So I think that's all I really wanted to say about that. I'll dig one up and we'll use another example of one from the database, and we'll see that you do get very broad peaks, which is a good hint of what it actually is. Okay, sulfur compounds. So there's a whole host of sulfur compounds. The thiols, the sulfides, sulfoxides, sulfonamides, sulfones, sulfonates. And we'll sort of go through these one at a time. SH stretch in the same area as the carbon-nitrogen triple bond or carbon-carbon triple bond. So you'll notice that carbon-hydrogen shifts are here, oxygen, nitrogen, hydrogen stretches are in this region, so it's shifted towards the left. This makes sense. Sulfur is a larger atom, more reduced mass, reduces the frequency. So that's why you see it shifted from where the OH and the NH stretches are to here. luckily, it's in a place where you don't see a lot of other things, so it would be hard to miss. In this case, we've got an aromatic, so all the same rules apply. You can look at the overtone region, you get the carbon-carbon double bonds, and then you can use the out-of-plane bends of the hydrogens to determine the substitution on the ring. So that's nice. Sulfides, you'll notice what's not in here is a carbon-sulfur bond. We're not, carbon-sulfur stretch, not a useful thing. So with sulfides, when you're actually changing this SH bond to a S carbon bond, it's just nothing useful. So look for, much like the ethers, there's not a whole lot to look for, but at least with the ethers, you have a carbon oxygen bond to look for here. So sulfides, this would be the functional group of last resort. Sulfoxides, however, have got a nice polarized sulfur oxygen double bond, and that comes out at around 1050. Now, of course, there's a whole series of sulfur-containing compounds which just are different based upon what this sulfur is bonded to. So if it's bonded to 2 carbons, you've got a sulfone. If it's bonded to a chlorine, you've got a sulfonyl chloride. If it's bonded to an oxygen, then a carbon, this is like a sulfonate, so it's like an ester, sulfonamide, and then the sulfonic acid. So the SO bonds will come in pairs because, of course, there's 2 of them. And you'll notice that they're basically in the same regions as each other. What you can look for next is that if it's a sulfonate or a sulfonic acid, you could look for the SO single bond. And if it's a chloride or a sulfonamide, the SCl bond is not useful, so you can't really look for that. But if it's a sulfonamide, the NH stretches and bends will appear where they normally appear. So you basically have to rely on those stretches and put them together in that fashion. So a sulfonic acid will, of course, have the OH stretch as well. So here's some examples. Sulfonate, this is an aromatic sulfonate, so you're looking for the typical aromatic overtones and out-of-plane bends, that sort of stuff. Your 2 SO stretches, and this is the SOR stretches here. With your sulfonamide, you've got your NH stretches in the around 3300. You can look for NH bends, but you've got your, again, your strong SO stretches here to look for as well. And of course, this is an aromatic, so you've got your out-of-plane bends and stuff down here. This is the last but not least, the alkyl halides. So carbon, chlorine, carbon bromine, carbon iodine. These stretches are all on the far right-hand side of the periodic of the infrared spectrum. The reduced masks is getting larger and larger and larger, so it's shifting it to the right here. You typically see these very broad peaks in this region, which correspond to these stretches. There is a hydrogen carbon X bend, which appears in this area, but often this area is obscured with other functional groups. So typically what people look for is these stretches first, and then you can look in this area for sort of confirmation. So I'll try to dig up some interesting examples and we'll put them together as an assignment, all right? Let me just turn my thing off.